Okay, good morning. Today I want to discuss a lecture on signal transmission under data communication and networking. So I want to see how computers that are on the network handle signals and how signals can be transmitted with high quality. Now let's begin by looking at, first of all, what does the word signal in this case mean? Signal simply means the presentation of data in some physical manner that can be either current, or voltage, or digital. So what you're saying is signals are just physical representation of data. So most computer networks, they use signals to exchange messages from one computer to the other computer. And you can see from the previous lecture how the ISO model can be used to filter and process the signal such that the computer can move the message from one PC to the other PC and the computer on the other end able to understand that message. Now, in this lecture, we want to see how this signal can be transmitted without disturbances or interference. Because signals are very important because they make computers understand what is being transmitted from one PC to the other PC. So if the signals are highly interfered or disturbed, you find that it will not perform according to the intended purpose. So we are going to see how these signals can be handled, more especially when we discuss the signal in terms of the data carrier or the message that we're referring to. So now, generally speaking, the signals makes use of the sine wave formula, which you can see below, where we understand these properties such as the frequency, the wavelength, and also the amplitude. But we want to focus so much not on these properties as how they work, but we want to see how these properties can help to boost the signal in such a way that it can be understood according to the intended purpose. So to begin with, a signal has these parameters that we modulate, as we say in the message, from one PC to another PC. These are amplitude, which is A, and the frequency, which is F, and also the phase, which is lambda. So you can see that these properties of the signal are moderated if the signal is carrying a message that you want to put on the network. So now it is these properties that we are going to work with to ensure that we've got high quality message being delivered to the destination computer. Okay. So find that there are basically two waves that you can consider. As you can see from the diagram here, we've got this diagram, the pulse wave, and also we've got the analog wave. When we talk about the pulse wave, we're talking about the digital signals that are transmitted from one PC to the other PC are referred to or are normally presented in the pulse wave, where we've got the lands, the peaks and the lands, where the peaks represent 0 and the lands represents 1. Now, it is these signals, the digital ones, which are converted into analog as you are transmitting the signal over the communication media, which makes use of the physical properties such as current or voltage to transmit data. So now, when the data is being transmitted, it is highly interfered such that the destination computer will not be able to get the data that is being transmitted. So now, to help us not to have this disturbance we are referring to as we transmit data, there are theories that we're going to understand and make use in this lecture. By the way, before we look at that, we must understand that the phase domain and the frequency and the amplitude in this case can be used to transmit data. What do I mean? If you moderate the frequency, you change the frequency, okay, to a normal frequency, you find that that signal is going to carry data. So Same applies to the phase. If you change the phase of the frequency or the phase of the wave, it means you are carrying the data. So basically, what we are saying is the signals that we are talking about can actually be changed in terms of these three properties. The lambda, which is the wavelength, you can change it. You can change the frequency. You can also change the amplitude if you want to send the data in signal. Now again, we are saying these same properties can be altered by outside forces which can cause interference. So now, as we look at the signal transmission in this regard, we would like to focus on the theories that can help us to transmit data without. But first, before that, let's look at the time domain concepts. An analog signal is one whose signal intensity varies in a smooth fashion over time. No breaks or discontinuity in the signal. Right. So that signal is actually referred as analog. Okay. And then a digital signal is one whose signal intensity maintains a constant level for some period of time, and then changes to another constant. We saw from the previous diagram where we had the lines and the bits, the zeros and the ones, are the ones that we are talking about as constant levels for a period of time. Right. So what we're saying is the frequency, okay, is a rate or cycle of the second, which is measured in hertz, as we'll see later on. And then the time is the amount of time it takes for one repetition of the signal, right? The lambda, which is the wavelength, is the distance occupied by the signal cycle of the signal. So these are the concepts of time domain that we're going to make use of. So now, let's see the sine wave parameters, the one that we've talked about. We have seen, okay, how we can affect the wave, okay, the frequency, the wave frequency, and how we can affect, okay, the wavelength from this diagram. You can also see how we can affect the amplitude. So this diagram shows the modulated waves, which carries data. So the secret behind message, okay, or signal is that if you modulate a normal wave, either by modulating the frequency or the amplitude or the wavelength, you are basically trying to communicate, carrying the message to the other computer. That's the secret behind signaling. It's just working with these properties that we have looked at in this lecture. So now the frequency domain concept, right? What are these? So fundamental frequency, we are talking about when all frequency components of the signal are integer multiples of one frequency, is referred to as a fundamental frequency. Spectrum, the range of frequency that a signal contains, right? Then the absolute bandwidth, we're talking about the width of spectrum of the signal. And the effective bandwidth, we are talking about now the band frequency at most of the signal's energy is contained. So any electromagnetic signal can be shown to consist of a collection of periodic analog at different amplitudes, frequencies. So what does this mean? It simply means that we actually need to have a clear message if we either increase the frequency, increase the energy, it means you actually have the good message transmitted. So the higher the frequency, okay, the higher in terms of quality message or signal. So we need to play around with the frequencies for us to achieve the high quality message. So if you don't have high frequency, you expect to have very bad message or signal being transmitted to the other end. So this is what you are referring to under the frequency domain concept. So increase the frequency, then you are going to have a better message conveyed. Right. So now what's the relationship between data rate and bandwidth? Remember we discussed data rate, the amount of data that can be sent in a second is data rate. And the bandwidth, we are talking about how wide or narrow the communication channel is. So now what's the connection? What's the relationship between the two, the data rate and the bandwidth? Suppose we look at these frequencies, F, 3F, and 5F. then we get a wave that resembles a square wave with 3 peaks per half. So what does this mean, people? It simply means that when you increase the frequency, the frequency has to correlate, okay? It has to commensurate with the bandwidth. So if the bandwidth is very small, you find that the frequencies will be reduced. Because if you're going to have higher frequency, you expect to have higher bandwidth. That's the relationship. So if you reduce the bandwidth, say by using one sign, okay, of frequency or 3F, we can achieve the same bit rate, but the signal has the higher chance of being misinterpreted. And it is actually what you are referring to as a bad signal. So you can see that the bandwidth and the data rate actually correlate, because the more frequency you have, you expect the high quality message that will be transmitted, okay, to the other computer. And also you expect that if you have a higher frequency, you expect less interference, because even if you're going to interfere, still the higher frequency can able to cushion the disturbance that you can. So in conclusion, any digital waveform will have infinite bandwidth, right? But a transmission system will limit the bandwidth that can be transmitted. That's the point there, right? So what's the channel capacity? So the channel capacity, we are talking about the maximum rate at which data can be transmitted over a given communication path channel under a given condition. So we must be mindful of noise as we discuss this principle of communication channel, right? So the noise basically is unwanted message. The message that we don't want, the unwanted signal, is what you call noise. So as you send the message, the desired message, you expect that that message can suffer, okay, a lot from noise, right? Which you are referring to as unwanted signal, which distorts the message you want to send. So there are theories that can help us to avoid or work with the noise as we look at the high quality message which need to be delivered to the destination PC. So now, there is Nyquist theory, which was actually introduced in 1912 by Nyquist himself. So now, this principle helps us to avoid noise or work with noise, because this one, he actually talks about if you double the frequency, you actually reduce the noise, or you cushion the noise. Even if you want to remove it, but you reduce the effects of noise. So as you send the data, you must endeavor to double the frequency of the message that you're sending. If you do that, you will reduce the noise or completely remove it. Right. So the higher the frequency, the lower the noise. That's the principle behind Nyquist. Okay. So if you look at to prevent all these problems we are discussing, you must be able to double or increase the transmission bandwidth. In that way, you are going to reduce the noise. So now, how do you handle noise? There's what you call noise signal to noise ratio, which is the SNR, which is actually calculated as follows: 10 base, okay, 10 log 10 signal power over noise power. So what's the principle behind this formula? So the principle behind this formula is the lower the noise, the signal to noise ratio, the better the transmission. So if the signal to noise ratio is closer to 1, is higher, we expect that this transmission has the highest noise. It will be interfered a lot. So you must endeavor to have a very minimal signal to noise ratio for you to have a better transmission. Right. So we use this formula to ascertain or determine whether there will be noise that won't be handled, that will distort the message at the end of the transmission. Right. But again, with Nyquist theory, there are some flaws that we have looked at. So if you double the frequency, quite right, you are going to handle the noise. But again, if the noise is too powerful, even if you double the frequency, sometimes it actually overtakes that principle. So in 1948, Claude Shannon introduced another theory which we are discussing right now. So that with this theory, you must able to increase the channel capacity as you want to endeavor to reduce the noise. So this theory talks about the maximum transmission channel, which should actually avoid the noise. So if the transmission channel is very narrow, of course you expect that you're going to have a lot of noise. So you must increase the transmission channel for you to avoid the noise. So with this one, there's a formula that we use, which is C, where C basically stands for transmission channel, and the B is bandwidth of 2 and 1 plus signal to noise ratio. And this is measured in bits, bits per second. So this formula helps us to understand how can have an error-free transmission in terms of noise. So the greater the capacity of the transmission, the more you reduce the noise. So you double pump the channel capacity for you to reduce the noise. That's the principle behind Claude Shannon theory. Right. So for example, assuming that the PSTN has the bandwidth of 3000 Hz and the typical noise to signal to noise ratio is 20 decibels. Determine the maximum theoretical transmission rate that can be achieved. Remember the formula? Okay, the formula that we just looked at is transmission capacity is B log 2, 1 plus signal to noise ratio, according to Claude Shannon theory. So just do a matter of substitution. We are taught from the question that you've got the bandwidth of 3000 Hz, just put there. And then you've got the signal to noise ratio, which is basically we are looking at we are looking at this formula here, which is the signal to noise ratio 10 log 10 signal power over noise power. So you can see the signal to noise ratio is basically what? Is 20. So we can do the computations from here, and then I'm going to have 100, which I'm going to substitute here. So once you compute this with the calculator, you discover that you're going to get 19,963 bits per second. Right. So assuming that the spectrum of channels between 3 MHz and 4 MHz, the signal noise ratio is 24 decibels. What is the bandwidth for the channel capacity? So you've got these, right, which were given. So the difference that you're going to have is the bandwidth, which is just 1 MHz. And then you need to solve the signal to noise ratio, which you're going to have 251 decibels. Then substitute in the Claude Shannon formula, which is this one, right? Which eventually are going to get 8 megabits per second. So how many signal levels are there? Apply this technique, right? To B log 2M. So remember, you've got the channel that you have, and then substitute, all right? So in this one, this computation here, I'm going to have 4. So all you need is to have M, which is the signal levels. So if you do your logarithm mathematics, if you remember those principles, this 2, this 2 will be raised to the power 4, which will give you, of course, 16 signaling levels. So I encourage you to revise a bit of mathematics in terms of logarithms for you to be able to calculate these formulas that were invented by Shannon, right? So people, what goes up must come down. I encourage you to watch the video once more to look at how you can actually understand these computations. And if you have difficulties understanding the computation, please take your time. Remember the logarithm principles and the indices in mathematics, they can do well to help you in this regard. So watch out for the next lesson. Probably that will be the last topic in your syllabus. We'll discuss the network errors and detection. Thanks very much.